Hello Year 8, this is your guidance video for Chemistry Week 7. Ramadan Kareem. We're going to try and keep these short because you're only supposed to have half an hour of learning during this blessed month. And so we're going to try and keep this very, very short. This guidance video takes up your time with the half an hour, so I'm going to try and aim for 15 minutes of guidance. And then the activities that you do should only take 15 minutes. We're going to have a 5-minute quiz right at the end for you to quickly fill on the Google Classroom, just for me to ensure that you have some really good understanding on the topic of temperature and the rate of reaction. Now, it's really, really important for us to appreciate that some chemical reactions happen almost instantly, such as explosions. And there are others like rusting or the corrosion that you get with acid rain, which take much longer. So there are several factors that can affect how fast or slow a reaction occurs. Now I'm going to introduce to you a theory called the collision theory. It's sometimes called particle theory. So for some of you, you'll be able to appreciate why it is that we have these effects of varying temperature on the rate of reaction using this theory. I'm going to show it to you through some animations. So the first thing I'm going to talk to you about is what a reaction rate is. So a reaction rate is a measure of how quickly a chemical reactant is used up. That's what you have at the start on the left-hand side of a word equation, or a product forming. So the rate of reaction is how quickly a reactant, which is a substance that reacts together with another substance to form a product during a chemical reaction, how quickly that is used up, or how quickly you make a new product. That's what you form in a chemical reaction, as a product. So let me just introduce to you collision theory. So chemists imagine that chemicals react as particles, and at Key Stage 3 we're quite lucky. We don't have to worry too much about the nature of particles. We don't have to worry about their shape too much when we're thinking about collision theory and particle theory. So we can pretend that these two structures are chemical reactants. Maybe there's one over here and there's one over here. You can see that they're moving towards each other. For a chemical reaction to take place, we imagine as chemists that these reactant particles, these are what you start off with. So this could be one of the chemicals in the reaction. The other chemical could be on the right-hand side. They must collide with each other. And what we also need to understand is that the particles must also have enough energy for them to react. Because if they just collide with each other, there's no guarantee that you have an automatic collision, automatic reaction, a successful collision, okay? So there's two things that we must make sure that we have to understand collision theory. One idea is that reactant particles must collide with each other. If they don't collide with each other, you don't get a chemical reaction. The second thing is the particles must have enough energy for them to react. If they don't have enough energy, they have an unsuccessful collision. But if they do have a successful collision, we have a chemical reaction happening. Now, the reason why they have to have a set amount of energy to as a result of adding up the energies of the two reactant molecules. The reason why we need to have a set amount of energy is because we need to overcome what's called the activation energy gap. And the activation energy is the minimum amount of energy that you find these reactants have to pay. They must have that. The colliding particles must have that amount of energy for them to react. If they don't have enough energy as a total, they cannot start off this chemical reaction. So it's the minimum amount of energy needed by particles for a collision to be successful. Now that activation energy depends on and can change depending on what type of chemical reaction you have. Some reactions have a very low activation energy, so those reactions are very easy to to progress. Others don't. Okay, so this is courtesy of the Bite-sized BBC website. Two pairs of particles, here we are, moving towards each other. You imagine that they collide. Now let's assume that they have enough energy to overcome that activation energy barrier. They collide, and what they do is they change partners. Remember the activities that we've been doing with the cards for balancing chemical equations? This now starts to make sense. So why it is that I chose that approach? Because the partners change and the pairs then reform so that each member of the original pair can join with a member of another pair, forming two more pairs. Now this is a nice simple representation of many of the chemical reactions that you actually come across in year 8. And then what happens is, once they've had a successful collision, it's bye-bye, we'll see you later, and that's it, they move away from each other. It's very rare for them to collide with each other and form back your original reactors, but sometimes that does happen, and those reactions are further investigated at GCSE. They're called reversible reactions. So, when we're actually doing a chemical experiment, we can monitor how quickly chemicals are made or chemicals are used up. And there's a lovely simulation that I'm going to ask you to look into this lesson. Okay, it's on the teachchemistry.org website. It's an American website. There's a lovely simulation on here called reaction rate. So I'll put the link in the slides and the lesson plan. So this will be task 2. Reaction rates. So what I'd like you to do is I'd like you to run the reaction. So click on run the reaction, okay? And you'll find that there is a graph that is drawn. Now, don't worry about that graph, okay? If you mess up, don't worry, just press reload on your browser and you can start it again. So here we go, reaction, run reaction, get a purple line. Now on the bottom you have time, and on the left-hand side you have amount of product. So your independent variable is time and your dependent variable is amount of product. Now, here what you need to do is you need to look on the left-hand side and see what's happening when you see run reaction. You can see that you start off with 2 reactants, they're blue and red, and they form a product, a simple product, it's a simple chemical reaction, form a product C, which is purple. Now what I'd like you to do is I'd like to select the variables. So what you have done is you've run a reaction for something that we want to compare, a chemical reaction for, but we want to have something to compare. So we're going to press run reaction again. You see exactly the same chemical reaction taking place. You can see the time is flowing, time's ticking, okay? And what I'd like you then to do is I'd like you to click on control, and it's a drop down menu. I'd like you to click on temperature. Now you have 2 choices. Okay. Now, what I'm going to ask you to do is I'm going to ask you to pause the video after I've given this question, and I want you to think. Now, this line here represents the rate of reaction. The rate of reaction is defined by the amount of product, as we have over here, made over a set time. Now, the rate of reaction is something that's very, very easy to read from these graphs, where you have time at the bottom and the amount of product on the left-hand side. And the amount, if it was as a gas, you could actually measure the amount of product as a volume as well, but more on that later. Basically, you can look at these graphs and you can think, if these lines are very steep, then you're producing a large amount of product in a short amount of time. If these purple lines are shallow and not steep, if they are gentle gradients, then you're producing an amount of product, a set amount of product, and it's taking its time to make that product, compared to running a chemical reaction and finding that the line is steeper. Okay? So what I'd like you to do in the next couple of exercises is I'd like you to try and predict, what do you think will happen if we change the temperature? Now this is a set temperature for this this chemical reaction. Let's pretend that this is room temperature for this chemical reaction. And we're going to decrease. I'm going to click decrease the temperature. So maybe we could actually do this reaction, but we're going to fill the surroundings with ice and cool it down. What do you think will happen? Do you think you're going to get less product and have a lower reaction rate? Or do you think you're going to, in a set amount of time, or do you think you're going to have more product being made if you cool everything down in a set amount of time? So the question I'm asking you is this. I'm going to ask you to pause very shortly. Do you think that you're going to have, if you decrease the temperature, a lower rate of reaction, which will then produce a gentle curve? Or do you think if you decrease the temperature that you're going to have a higher rate of reaction and this line is going to be steeper? Do you think it's going to be a steeper line if we click decrease? Think about it, pause the video, and then play when you're ready to carry on. Well, let's find out. Let's decrease and then run the reaction. So you'll find the reaction takes place much slower. The particles, this is your explanation, this is because the particles are moving faster than before. They have less stored energy, movement energy, than before. So you can see that not all of them are reacting successfully. We have fewer purples than we did before, fewer purple product particles. Some of the reactants A and B, blue and red, are still there. It will take more time for us to make that amount of product compared to when we had a higher temperature. Now what we're going to do is we're going to put it in a very hot environment. We're going to heat it. We could boil the liquid. We could add some heat using a Bunsen burner. We could place it in a hot place. We can place it in an oven. What's going to happen to this purple line? Is it going to show just the same as what we had before? Is it going to show a gentle slope, showing a decrease in reaction rate? Is the reaction rate going to be lower? Or is the reaction rate going to be higher? Are we going to have a steeper line now compared to this room temperature reaction? Let's think about it. Pause the video and play when you're ready. Well, let's increase the reaction. Now remember, this was what was happening at room temperature. As time went by, we got this amount of product being produced. Let's run the reaction. You'll notice that they're moving much faster. So there's more stored kinetic energy in the particles. They're moving much faster. And the collisions are happening in a smaller amount of time, in a shorter amount of time. And because the particles are moving faster as well, you're getting more successful collisions taking place over time. So as a result, the amount of product that you make over time is much higher when you raise the temperature than when you had it a lower temperature before. So I'm going to start over again. This was the control. I'm going to run the reaction. This was at room temperature, and you can see that's nice and casual and steady. But if we then raise the temperature, we get a faster set of particles, more successful collisions, product being made in a shorter amount of time, a steeper line on this graph of time versus amount of product, and a higher reaction rate. Whereas if we lower the temperature, run the reaction, we have a shallower slope, a lower rate of reaction, explained by the fact that the particles are moving slower. There are less successful collisions over time compared to a higher temperature. And not all of the collisions are successful. So you still have some reactants left. And they're not all successful because the activation energy cannot be overcome and your particles cannot provide that activation energy for a successful collision. Thanks for watching. Enjoy the quiz. Stay safe and Ramadan Kareem.